we're going to cover a new data structure that is kind of less known. It will be the segment tree. So let's recap what we saw in the last session. So the last session we addressed the problem. We said that we have a series of queries, or we have an array A. So we have an array A with values v0, v1, etc. till vn. So this array could have arbitrary values initially, and we have a set of queries where each query is in the form of li, ri. You have a set of queries, and each query is asking us to compute the sum of a range from li to ri. So the sum of the range of the values inside the array A, inclusive from li to ri. So we saw a naive procedure to solve this, which is actually oh, wait. Which is O Q, the number of queries multiplied by n, meaning that for each query that we have, we need to just loop from li to ri and sum up the values in the array A. And then we saw a simple trick, which is the prefix array, which will pre-compute the sum of prefixes in on initially, and then for each query we will answer the query in o1. I could explain this again later if you missed this part. This is very trivial. The prefix array is actually a trivial trick. This is nothing. But now we will look into a very, very cool data structure that will enable us to answer the same queries. But in addition, it will enable us to answer the queries even if there is updates to the ranges. So again, we saw also the row measure representation and matrix sum, which is just a more general form of the prefix array. Actually, I wanted to say something here. I made a mistake when I was reading the quiz again. I saw that I made a mistake in the statement. Here I actually wanted to ask the maximum sum of square matrices. I'll make the. So here it should be a maximum square surface, not maximum rectangular surface, which will change the complexity. I'm willing to explain the solution for the problem later, but here actually it's not rectangular, it's a sum query. If you read the entire description of the problem, you would understand that I made a mistake here. I was meaning a square. Parathash is here. Hello. So if you have questions, as I said, I would explain from scratch. But if you didn't understand or you missed the last part, don't worry. You could read it on your own and ask me questions later. This part is very, very different than what we saw initially. So again, let's ask the same question. We have an array A. So we have an array A of arbitrary values inside. Now we have queries Q, where a query can be of two types. It could be either a query in the form 1 L R, or it could be in the form 2 I V. So what is this? What's the meaning of the two queries? The first query is the same as what we seen initially in the prefix array. This query means that we need to sum up, or we need to compute the sum of the values in the range LR and reports back that sum. So this was it was possible to do this with the prefix array in O1. Again, if you forgot about this or you missed it, it's no problem. We're gonna look into a very different approach that is much more practical. And the second type of queries on the same array that we are computing the sum. So we have two types of queries. We have a big number of queries. Sometimes we have queries that asks us to sum up the range. And other times we have queries in the form 2IV, which means assign the value at position I, the value V. So this query is just asking us to place in the position I the value V. We're just changing the value from what it was to a new value. So the prefix array, what's great about the prefix array, it's very simple, but it doesn't enable us to change values in the array, meaning that once we compute the prefix sum of the entire array, if we change a value at position I, we have to change all the values from I up until the last position. So that this updating a single value in the prefix array would be ON. So the prefix array is efficient to compute the sum of the range, but is not efficient when there is queries that require updates. Okay. Now we will look into a very different data structure, a quite unconventional one, but it's actually really easy to understand. So another thing is that the prefix sum, it would work for XOR. For XOR, there is no issue. If you have you need to compute an XOR of a range, it would work. Of course, if you don't have updates, this would work. The product, if you don't have null elements, if you don't have zeros inside, this would work. Product. But that's it. We might be interested in knowing the minimum of a range, meaning that we have A. As I said, we have an array A. And we might be interested in finding the minimum of a given range, just that given range, LR. Even without updates, the prefix array would not work with the minimum and the maximum. There are other like there is another structure called the sparse sparse array. Sparse array, yes, sparse array. There are other structures like the Fenwick tree, but the most general data structure that enables multiple operations and it's much easier to explain is the range query, which is just another array. It has nothing more than an array. So let's take a look. So suppose that we have an array of n elements, and let's just suppose that we have an array where the number of elements n is a perfect power of 2, meaning that n is some power of 2, 2 to the power of j, where j is an integer. Okay, suppose that we have an array, and this array is what is the array that we want to compute. Is the array that we want to answer those queries. So this is the array A that we was talking about initially. So let's suppose that A has a size that is a power of 2. So a segment tree, ST, or a sum segment tree, because right now we will just stick with the sum operation. Then after, I would show that you could generalize this to any operations like minimum, maximum, XOR, and it would work. So is an array of size 2n. So if we have A of size n, ST would be an array of size 2n, double the size of the array for which we want to answer those queries, where n elements. So this segment tree is an array, and the first thing is the elements of the original array. So the elements of A will be placed from n to 2n minus 1. So we have from 0 to n minus 1. Initially, we have empty values from 0 to n minus 1, and the values of the original array A will be placed from n to 2n minus 1. Okay. So that's actually this array is the segment tree, and we will look right now into how to build it. So a segment tree, as I said, has the elements of the original array A at the end, or has the elements of the original array as a prefix, or half of the segment tree is the original array. Sorry. Okay. Okay. And for each element at position I, where I is between 1 and n minus 1. So again, let me clean this mess up. We have the elements of the original array from n to 2n minus 1. And the elements that are from 0 to n minus 1. So I would be, when I say I between 1 and n minus 1, I'm talking about these indices. For each element in this part of the array, sti sti equals the sum between sti multiplied by 2 plus sti uh, multiplied by 2 plus 1. So let's just see what this would yield. I will just show a simple demonstration here. No, I just said that the segment tree is this entire array of 2n. We have the original array A as a prefix of this segment tree. The exact values are placed from n to 2n minus 1. And the indices here, so each index here from n minus 1 to 1, a value here, sti, it will be equal. So, for example, the value n minus 1 here, st n minus 1, it would be equal to it will be equal to st 2 multiplied by n minus 1. So this is the I plus st 2 multiplied by n minus 1 plus 1. This is the formula. So the values in this range of positions would be equal to the value of the array at the indices doubled and doubled plus 1. So this is for the sum, just for the sum. That's because we have a segment tree that would answer some range queries for now, at least. So let's just take an example and see what this would look like. Um, let's not do this. Books. Segment tree. Segment tree. Segment tree. Okay, for starters, let's just take this part of the code and see what it would give. Okay, let's just take the first two procedures. So what the code here is doing, we're just creating a class. This is the array for which we want to answer the query. So this is A. The segment tree, this is ST. This is the segment tree, ST. ST equals length of the array multiplied by 0 plus array. So we are creating an array of double the size of the original array. The first half is just zeros, and the second half is actually the original values in the array. Here we are placing in the first element of the segment tree, or element 0, we are placing none, nothing. This is not clear why, but this doesn't matter. I could just erase this instruction and it wouldn't matter. So size is the size of the original array. I could just, for clarity's sake, let's just write A. Okay. And then we invoke this procedure, fill segment tree, which does exactly this. For each position I between 1 and n minus 1, we fill the segment tree at position I with sti multiplied by 2 plus sti multiplied by 2 plus 1. I hope that this is at least, there's nothing suspicious, but once we execute the code, you will see what's going on inside. So I will just create a simple array or from random import random a equals. So I'm creating a simple array int random multiplied by 100. Random I in range. Let's just take a simple power of 2. Let's just take 8. I said initially that the size of the array needs to be a power of 2, so I took 8. We will discuss what to do if the array is not a power of 2 in a moment. So this is an array, and we just want to compute sums of ranges in this array A. Okay, so let's create a segment tree based on this array. So we pass A, st, print st dot segment tree. Okay, let's print A also. A equals st equals. Okay. So this is our original array. This is the array for which we want to compute queries that are either updates or range queries. So you could see that A is placed at the end. Sorry, it's placed at the end here. The values of A are here: 69, 30, 33, 8. 58, 81, etc. This value is exactly, so this value is st n minus 1, right? This is at position n, this is at position 2 n minus 1, this is st n minus 1, and here n is equal to 8. So this value is or st n minus 1 by definition, we said that it's equal to st 2 multiplied by n minus 1 plus st 2 multiplied by n minus 1 plus 1. So if we replace here n is 8, right? So if we replace n by 8, it will be st, let's just, so st at position 7 is equal, so this at position 7, let's print this, 62. So 62 is equal to st at position 2 multiplied by 8 minus 1 plus st 2 multiplied by 8 minus 1 plus 1. So this is the same. We are, this value is the sum of the two values, same. This value is the sum of this and this, same. This value is 66 is the sum of these two values, etc. 53, so 53 plus 69 would be equal to yeah, 69 plus, this is accurate. So each, wait, yeah. Okay, from 366 to 134. Okay, I said that 134 is look, 62 is 62 is 14 plus 48. This is position n minus 1. This is at position n minus 1. We said that elements of the original array are placed from n to 2n minus 1. This is the original array, right? And values at position I from 1 to n minus 1 sti equals st 2i plus st 2i plus 1. So this is equal to 14 plus 48. You could check. This is this. This is this. You could check again. And now this is the sum of these two values, 62 plus 100, and this is another I which lies in the range 1 to n minus 1. So this 196, which this position is what? 0, 1, 2, 3. Look, this is position 3, right? So ST position 3 and ST position 2 multiplied by 3 plus ST at position 2 multiplied by 3 plus 1 is the same. Okay, so 171 is this sum. And the 366 is this sum. Okay, so actually this is a tree. This is a tree where each node is represented by an index in the array. So values at a value at position I in this segment tree or this array have two children. A child at position 2 multiplied by I plus 1, and the child at position 2i. So these two are the children of 62. These two are the children of 134, etc., etc. These two are the children of. So this is actually a tree, or this is called an implicit tree, because we don't have pointers to the children. We just access the children by multiplying I by 2 or multiplying I by 2 plus 1. So each element from this is a tree where each element between 1 and n minus 1 is a node in the tree where the children of this node are at position 2i plus 1 and position 2i. We could actually access the elements directly without explicit pointers. So what we're doing is we are creating nodes of a tree where each element will represent the sum of a range. This element represents the entire sum of the entire range. This element would represent the sum of this range. This element will represent the sum of this range. Same, this element will represent the sum of this range. This element will represent the sum of this range. And then this element would represent the sum of this plus this, which is the sum of this entire range. All right. We agree that this 196 is the sum of these two. All right. This is position 3. This is position 2 multiplied by 3, and this is 2 multiplied by 3 plus 1. So this is actually the sum of this entire range, because this is the sum of the first range, and this is the sum of the. So actually, each position in the segment tree represents the sum of a complete range. Okay. So let's change this just a little bit. Now we are interested in the sum, right? We are computing the sum, but what if we were computing the minimum? So we just have to change this to the minimum. or we would, if we were interested in the max, it would be the same. So look, the minimum between these two is 14. The minimum between these two is 21. The minimum between these two is 11. The minimum between these two is 26. Again, the minimum between these two is 21. The minimum between these two is 11, and the minimum between, okay, it would right now with this structure, it would we could compute minimums or maximums of ranges and other operations, of course. Okay. So this procedure, fill segment tree, is just counting down from size. So we are going from n minus 1 to 1, because the 0 is not included, and for I from n minus 1 to 1, and for each position we are computing the sum of the right child and the left child. Actually, I said that each element at position I is a node that have two children, one at position 2i and one at position 2i plus 1. We call the child at position 2i as a left child, and the node at position 2i plus 1 as a right child. Okay, so right now we just constructed this this tree, but for now we don't know how to how should I say this? We don't know how to compute the sum of ranges. We could compute the sum of a range easily if we have like a range that is perfect. Like, let's go back to the execution. If we wanted the sum of a range that is from like this range, I mean, we take directly this this value. If the sum of the range starts at a, well, I'm gonna explain, but you might not understand this. But if the sum of the range, if we had a range that starts at a left child and has a power of 2 as a length, we could just get the appropriate node and return it. But for now, we don't know how to compute a range if it's like if it's the sum of this range, for instance. We don't have a node inside the tree that represents the range 0 to 2, for instance. But we are close. So is there any questions for now? Okay. Okay. So let's say that we have this again. I did the example. Let's say that we have this array for 14, 8, 5, 0, 7, etc. And we want to create the sum segment tree of the array. We would have this structure. So 14 plus 8, or 14 would be placed at position 8. This array is of size 8, right? You could check. So 14 plus 8 will give us 22 at position 4, because 4 multiplied by 2 will give us 8. Plus 1, it will give us 9. So at position 4, we will have 22, etc. 5 plus 0. Okay, so we actually have a tree structure, but it's represented as an array. Okay. As I said, the element at position 0 is unimportant. We will not use it. The element at position 1 represents is the root of the entire tree. So if we 1 multiplied by 2 and 1 multiplied by 2 plus 1 is the immediate descendant, or the immediate children of the highest root. And another thing, if we were at an arbitrary position, like if we were at this position 5, or better yet, if we were at this position 13, arithmetically, how could we access to the parent? Can someone answer? I know that some of you are familiar with the structure.
By 2.
Divide by 2, yes. So we divide by 2. By dividing by 2 and taking the integer, so we take the integer results of the division, not
Floor
6.
value.
Floor value, yes, floor value. So, or the integer, the exact division. So floor value 13 divided by 2 floor. This operator is the floor value, meaning the closest, the nearest integer smaller than this quantity. So this is 6. So we would access 6 directly. At any position, we could try this. At 7, 7 divided by 2 floored. Floored. It will give us 3. 6 divided by 2. So if we want to access, as I said, if we were at a position I, and we want to access children, we just multiplied by 2, and we get the left child. If we multiplied by 2 and took the value plus 1, we would access the right child. So again, with this convention, all the right childs will have odd indices. This is a right child because it has an odd indices. Odd index. This is a right child. 5 is a right child. You could see this. It's a right child. 3 is a right child. 15 is a right child. Whenever we have an odd indices, it's a right child. If we have an even index, it's a left child. And we can access the immediate parent just by dividing by 2. Okay? So let's start with the update rather than the range sum. So as I said, if we have a prefix array, the range sum would be constant time, but the array must stay static. But if we have updates, then we have to update the entire prefix array, and it would be O(n). But right now, if for instance we place here a value 6. What do we need to update? We don't have a prefix to update. We just have to update the values in the path to the root. So whenever we update a single value, we just have to walk up to the root and update all the value in the way. And how we walk to the root, we just divide the position by 2 until we reach the roots of the segment tree. So whenever we have an update position right now, we change that value and walk up to the roots, updating each position in the segment tree until we reach the final node. So this is log n. Right now we have a structure that enables us to update in log n time rather than in O(n). So let's take a look initially at the updates before we look into how to compute the range sum. It's log n because this is a tree structure, and it's a complete tree structure. So I say log n because the path from, look, if we want to update a value and we need to walk until the root, what we will do is we will divide the index by 2 multiple times. So how many times we could divide the index by 2? Log n time before we reach 1 for any value here, like even 15 divided by 2 divided by 7, then we divided by 2 a second time, then we divided by 2 a third time. So at most the indices is at most 2n minus 1, right? EE. So at most the indices is 2n minus 1. This 2n minus 1 we could divide it by 2 at most wait, log n plus 1 time. Let's ignore this minus 1. How many times we could divide n by 2? We could divide it by 2 at most log n time, right? And we have this 2 factor, so we could divide it by 2 log n plus 1. We can ignore the constant factor as in the complexity explanation, and we just keep the log. We just keep O log n complexity to update the path from any arbitrary position I to the root. Okay. Okay, so what we do is let me look at the code. So we have this structure, and we call the update. So st sc update. We will update the value at position. Let's make the value smaller from 0 to 10 and update the value at position 2. And see what's happened. Oh, it's position 2. Let's place. Let's take this example rather than taking an arbitrary array. Let's take this array. So A equals okay. Exactly 3 values. So what should we update? Here we are taking actually we changed the segment tree to be a minimum segment tree. Let's change it back to the sum. And at position 0, we would at position 3 we would place the value 100. Okay. At position 0 we'll have 100 instead. So here is initially the array. Here is the segment tree. So at position 3 or at position 2, so this is the array. This is the value at position 2. So this 5 was replaced by 100. And we updated the value. So see, we divide the end. This is initially at position 2. So 2 plus the size of the array, 8. This is at position 10. You could check this if you want. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is at position 10. 10 over 2. So we access the value at position 5, 0, 0, 1, 2, 3, 4, 5. Okay, 100 because 100 plus 0. We divide by 2, so we are summing 22 with 100, and we continue. So this is the right sum. If you check, the original sum was 63. We replaced 5 by 100, so 63 minus 5 plus 100. It would be 58 plus 100, which is 158. So this procedure actually work. And how we do this? We said that the values of the original array are placed at position n. They are placed at position n plus. So if we want to update the value at position I, for our example, it would be 2. We would sum the size of the array plus the position to be updated. So n plus whatever the position in the original array. So to access the value in the segment tree, and we assign it to the new value. So A equals the position. So this A is, again, I said that the original elements of the array are placed from n to 2n minus 1. So if we want to access the value of the original element. In the segment tree, what we do is we shift the value of the index in the original array by the size of the array. So A equals this expression, n plus, this is the n. And while I superior to 1, I superior to 1, pardon me. Oh, okay. Well, while I superior to 1, exactly, because we are updating actually the parents. We are updating the parent and then dividing by 2. So while I superior to 1, so this is actually saying as long as we are not at the root, because when we have the index 1, we are at the root of the segment tree. B equals I plus 1. If I modulus 2 equals 1, so this is actually what we are testing right now, is if I is a right child. You are testing if I is a right child in the segment tree. If it's a right child, then we shift, because we want to have I as a left child and have B as a right child. In other words, we have the index I that we want to update the parents. So let's go back to the drawing. We updated this element. Initially, I would be 8 plus 2, so A would be 10. So when we divide when we update the value of the parents of A, what we do is we add the current value of the segment tree at position A plus, so we sum up STI plus ST wherever the node that is in the same or whatever the node that is linked to the same parents of I. I don't know if I'm explaining this right. Let me simplify this. So we want to update a value at position A, right? In our example, A was 10. 8 plus 2, which is 10. So when we need to, in this specific example, let's just forget about this. In this specific example, when we want to update the parents of A, we want to put the value at the parent equals to the value of the two children summed up. We want to have ST A divided by 2 equals ST A plus ST the other the brother or the element that is attached to the same parent of A, but we don't know if A is a left child or a right child. So to know whether A is a left child or a right child, we will just check if a modulo 2 is 1. If a modulo 2 is 1, then a is a right child. So if a was this, a is a right child, and we want to update. If a is a right child, we want to do this. A st of a equals st again if this is a right child. This is the formula if st was the right child. If it was a left child, we would do this. St a over 2 equals st a plus the right child plus 1. So we want to know how to access the other node that is attached to the same parent of A. And this is exactly what we're doing here. We just test. We initially assume that A is a left child and take B as A plus 1. So B is the right child. But if we test A and we found it to be the right child, then we switch. We take B as A and A as A minus 1, and we update the parents. Then we divide by A. Whatever A is, it's a left child or a right child. When we divide and take the floor, or we take, this is actually written in Python too. So if you use Python 3, you should be aware of this. This is not this would give you a floating number. So this is actually Python 2. So we just access the parents, and that's it. So again, initially we are at this position, and we test if A is a left child or a right child. It's a right child, so we take we take A plus 1 and A and sum up to get the update here. And then A is this right now. It's once we divide A by 2, A is 5. Now A is a right child, so we need to access the left child that is attached to the same parent, not access the other right. So if we do A plus 1, we would be accessing this, which is false, which is wrong. So we access the left child. Here again, A is a left child. We access the right child, and that's it. So this is all the updates operation. I hope. Okay. Yes. Here. Yeah. Before we update the parents, before we update the parents, we just test if A is a right child. If it is a right child, then we switch. We take B as A and A as A minus 1, so that we have the right range. That's it. If A is a left child, then we do nothing. B will be the right child, and A is the left child. Okay, it's clear. So this is just the update operation, and it's clear that it runs in olog n time. So this is actually an improvement over the prefix array. So now let's do the other type of query, which is the query that asks us to sum a complete range LR. So let's take the code. So to sum a range between L and R, so let's access the values, or let's create the indices that represent L and R in the segment tree. So to do that, we just shift that element by the size of the original array, self-point size, self.size, pardon. So a b equals self.size plus L. So this is the left child, assuming that L is the smallest indices, and B equals R plus, this is N, the size of the original array. So we are accessing the indices of those values that are in the prefix of the suffix tree. So while I inferior or superior to B. This might look trivial here. We have two indices in the segment tree. One is a left bound of the range that we want to sum, and the other indices is the right bound of the range that we want to sum. So while I inferior to B, so as long as I is not superior to B, or as long as as long as I is not superior to B, so we're basically saying as long as the range is not null. We will come back to this just in a moment. So if the right bound A is called the right bound of the range, left bound, left. Let me stop the recording just to save it, and then I will start it again. Can you? I have to take just a few minutes. I'm coming back. Just 5 minutes. I will be back. I'm just saving the video, so I'm afraid the computer will crash and I would lose the entire video. So I'm saving it just a few minutes. It will complete and then we will continue. If you guys have any questions, um, um I would like to hear from you guys that what are you guys interested in in especially in data structures like uh what uh what algorithm would you like to see next, like especially graph algorithms with I don't know, maybe you would like to see the Floyd Warsaw or something heavy light decomposition. Karthik, Parthesh, yeah. Oh, oh, red and black trees. But balanced binary search trees usually you just use the one implemented in the with like uh, the built-in data structures in the language are usually what you use. So you would like to understand the entire structure rather than black trees. Yeah, yeah, but you're used to using a balanced search tree from the library or yeah. But usually even in like competitive programming, usually we don't implement it. The red black tree is interesting. Yeah, maybe I think we would do it, but I don't know. It will take time because it will take no. I think we would do it. I think we would do it. Even if we won't do it like a course, I would do it just like just optional for people that are interested. Like the balancing and coloring the links between the nodes is actually a little bit difficult to explain. Actually, balancing is not very difficult, but usually you just use the the tree map from the standard library and you're good. The only problem is if you have if you have like duplicate keys, and there are operations that are very interesting that you could implement that are not available in in the standard implementation, like the rank of the key, or how to handle duplicate keys, even if you don't insert the duplicate keys, how to implement. You're used to using a heap, or heaps or priority queues. EE. Yeah, it's almost done. I'm just gonna launch a new recording. Yeah, I tried. I tried to play APB like 2 days ago, and I get obliterated. I haven't played it in a very, very long time, so I looked like a noob. I just quit, immediately exited the game. It's been a very long time, and my computer is struggling with a game from 2012. Oh, oh my, it's not a bad computer. It's the game that is very, very, very frustrating. Yeah. Okay, let's just start another recording. Okay. Okay, we got it. Let's make this a little bit bigger. Okay, let's start. So, we said that when we are computing the range, we put A to be the left bound of the range, meaning that A is equal to n plus L. So we are accessing the index of the uh, or the left index of the range in the segment tree, and B is n plus R. So while the range is not null, or while A is inferior or equal to B, if A modulo 2 is equal to 1, this means that if as I said earlier, if A is we are testing if A is a right child. We are testing if the left bound of the range is a right child. In this case, the left bound is a right child. And here we are testing if the right bound is a left child, if B modulo 2 is equal to 0, meaning if it's a left child. We said that initially elements and indices that are even are left child, and elements at indices that are odd are right child. Okay, so why are we doing this? Let me show you why. So see here, if we took a range like here, for instance, from 12 to 15, or rather yet from 8 to 15. So this is the entire range. This is the 63 that is up above. So we don't have to worry about whether A is a right child, or B is a left child. If we took the entire range, we just walk up the tree. We just walk up the tree. We just divide A by 2 and B by 2. until we arrive at the root. Because here, for the entire range, of course, if n is a power of 2, for the entire range, we just keep dividing the indices by 2, and the left bound will stay as a left bound, because the left bound would be n, and this would stay as it would stay odd for the entire time, because this is 2n minus 1. So this will always be even, however long we divide by 2 to the power of some k. It will stay even because n is a complete power of 2, and this will always be odd. Okay, we don't have to worry about anything. But suppose that our range is this. Oh, I can't go back. So suppose our range is this. So this A here is a right child, because it's 11. It's an odd number. Let's make it more interesting. And the B is this. B is a left child. So if we just divide A by 2, we would be accessing this parent, right? And this parent is not in the range, because it's not in the range because this parent would include both A and A minus 1, and A minus 1 is not in the range. Same if we divide B by 2. B by 2 would access 7, and 7 includes both B and B plus 1, and B plus 1 is not in the range. Okay, so if B is even, meaning if B is a left child, we add the value at B and decrement B to access the sibling of B to the left. Same if A is a right child, sorry for the horrible writing, child, we add the value at position A and access the right sibling, meaning that access the value to the right. And we divide A, of course, we divide B. This is a little bit difficult to see, but what we essentially are doing is, if A is a right child, we have to exclude the elements to the left of it, because if we just divide A by 2, we are including the elements to the left of it. Same if B is even, if B is a left child, if we just divide B by 2, we are including the element to the right of it. So to exclude it, we just add the element of B, because B is in the range, but the element to the right is not in the range. If B was odd, like if B was 15, we just divide by 2. We don't have to worry about anything, because the parent would include both B and the left child. So this is what we're actually doing here. We're just testing if A is a right child. If it is a right child, we add the value at A and access the right sibling. If B is a left child, we add the value at B and decrement B to access the value of the left sibling. This is a little bit difficult to see, but when we see the example, it will be a lot more clear. So, and we divide A by 2 and B by 2, but to access the parents, of course. Again, we add elements to the sum of the range only when A is odd or B is even. Only if the left boundary is only if the left boundary of the range is a right child, this condition, or if the right boundary of the range is a left child, this condition. This is the only two instructions that change the range of the sum, and then when A is superior to B, we just return. Okay, so let's take an example. So the easiest example would be to take the easiest example would be to take the entire range. So let me bring the code just to the left and see what are we doing exactly. So here we are computing L equals 0 and R equals 7. So here A equals L plus N, so A equals 8, and R equals 7, B equals 8 plus 7, so it will be 15. Okay, so this is the range that we are computing, B, A. So what we do is we test A. If it's a left child, we test A modulo 2, whether it's 1 or here A modulo 2 would give us 0 because it's 8. So we will ignore this. Nothing would happen here. Same we test B if it's a left child, modulo 2 equals 0. This is false, so this would be ignored. So the only thing that would happen here is that we divide A by 2 and B by 2. That's it. So we divide A by 2. So 8 divided by 2, it would be 4. And 15 divided by 2, it would be 7. So right now, B equals 7 and A equals 4. For now, range sum is null. There's nothing in range sum, it's 0. So again, we test if A is a right child, which is false because A is even. So we will not execute this again. And we test if B is a left child, which is false because 7 here is 7 modulo 2 is 1, so this won't be executed. Again, we will just divide A by 2 and B by 2. So again, B would be 3 and A would become 2. Again, we would test if A is even. If A is odd, A is not odd, it's even. So nothing would happen here again. And B is odd again. So we would just do the same. Just divide B by 2 and A by 2. Again, up until now, we have not yet updated the value that would represent the sum of the range. So right now, A is 2 and B is 3. So we would divide B again by 2. So B would become 1. And A would become 1. So right now, B and A are pointing to the same element. Right? Okay. Right now, something interesting would happen. A right now is a right child because A modulo 2 would be 1. So we would execute this. So we would add the value at the segment tree at position A to range sum and increment A by 1. So right now A would become 2. B would not do anything because this is false and the B is equal to 1. So this would not get executed. So we would divide A by 2 again. So A would be 1 and divide B by 2, which is 0. And now we would stop because A is superior to B. And we have the range sum because we just updated it in the last instruction of the loop. So this is a very simple, the most simple example. Let's now take something more interesting like this. A equal like R equal to L equal to 0, 1, 2, 3, so 3, and B equals to 7. So initially, R equals to 7. So initially, I would just write here A equals to 8 plus 3, so 11, this. And B would be equal to 7 plus 8, which is 15. So this is A and this is B. So we will test A. If A is odd, it is in fact odd. So since A is odd, we will add the value at position A to the range sum. So we will add this 0 to the range sum, which is insignificant because it won't do nothing. But the most important thing here is that we will not access the parent of A. We will increment A by 1. B this would not execute for B because B is odd. So we would this is false. So this would not get executed. But imagine that we did not do this instruction a plus 1. So if we divide a by 2 here, we would access this element 5, which is outside of the range 3, 7, right? Because this element represents both, or this parent represents both the elements at position 10 and 11. So we are going outside of the range. To stay inside the range, we need to update a to a plus 1 to access this. So this is what this instruction is doing. It's excluding the left child of the parents of A. So because it's outside of the range. Otherwise, if A was even, then we could just divide. It's not an issue. So this is the difference here. We just add the value. If we had something else other than 0, it would have made the difference. But at least we are not updating A in an erroneous way and taking a value that is outside the range. So here A will take value 12 by this incrementation. And then when we divide A and B by 2, we will have A equals to 6 and B equals to 7. So we are here right now. Okay, again, I added the value at A. Before ending the loop, we added the value at A. Okay, now we will test if A is odd, which is not the case. So this would not execute. If B is even, this is not true because B is actually odd here. So what we would do is just update A to A over 2 and B to B over 2. So we will have here 3, 3. And now, again, we are at A and B are at the same position. So when we execute this this instruction, A is actually odd here. So we will add the value at position I. So range sum here would be equal to 36. And this would not execute because B is odd. I forgot something. We need to execute A plus 1, so A would be equal to 4. And then we divide A and B by 2, so we will have, in the next iteration, we would have A equals to 2 and B equals to 1. And we stop because A is bigger than B. Okay, so we are actually computing the range sum in O log n time. The prefix array enabled us to compute the sum of the range in O1, which is very, very good, but the update was, it was impossible to do updates with the simple structure. But here we are both updating and computing the range in log n time, which is very, very good. So of course, this is log n time because for the same reason that we discussed earlier, at most B would take, at most A and B would take the values to n minus 1. Actually, if A was to n minus 1, this would be constant time because at the first instruction we would hit a situation where A is superior to B, and you could think about this by yourself. But at worst, the worst case is when B is 2n plus 1 and A is equal to n, and we are just dividing A and B by 2. So at most we would be dividing B and A log n time plus 1. So this is log n. So this is actually a very, very cool structure, and the best part about this structure is that it enables in most of the types of operations that take two elements, like min, max, XOR, a sum, product, anything, and you could take just that implementation you could just take the implementation as it is, and instead of well, in the lecture notes, if you saw what I wrote. So if you read the lecture notes carefully, I said that the advantage about the segment tree is that it enables multiple types of operations, and it's easier to understand. There are other data structures that are very similar to the range query, but the most well-rounded data structure is actually the range query, the segment tree. So if you were to implement a segment tree for different operations that take two values of two childs and compute the value of the parent, so we will take the value at position I multiplied by 2 and I multiplied by 2 plus 1 and compute the value at position I. If you have some operation, let's call this OP, then you could make a range query for this operation. And in the generic segment tree code that I put in the lectures, in the reading material, instead of like hard coding the operations, the operation is passed actually as a function in the code, and instead of doing like here plus or XOR or min or something, you just pass the operation as an argument to the constructor of the range query, and then call that operation on the left and the right child, and you have a range a segment tree for any type of operations that you could define. Of course, the default elements here depend on the operation. For instance, if you have minimum, if you have the minimum range, if you have a minimum segment tree, instead of using a zero value for the range value, we would take minus infinity as, because here in the range query, if we had a minimum range query rather than a sum range query, so when we take the minimum between values, if we initialize the range value to zero instead of doing minus infinity. Minus infinity, of course, is just in Python. You could just write floats minus inf. Or if you're using Java, you could just do wherever the type integer dot max value. Or double dot max value or something like that. Pardon, I made a mistake. For the minimum, it's plus infinity rather than minus infinity for the minimum. For the maximum, it would be minus infinity rather. Same here, integer dot max value or integer dot min value is the same. Okay, so what I was trying to say is that you could have a different default value depending on the operation that the segment tree is supporting. So you could just define a default parameter, default value that takes 0 by default, and if you have a parameter that is actually different than 0 for that operation that you are using, for instance, the product default value would be 1. So if you have a default, another default value, just pass it through. And this is functional programming because we are passing to a function another function operation. So if this is a little bit weird, just let me show you what this looks like in an example. So we are clear that this is the same code as in the normal segment tree. The only thing that is different here is that we are specifying a default value based on the operation and an operation as a procedure. And we are creating a member attribute or an object attribute operations that would take the operation. So this is a function actually that we are assigning. If you're familiar with JavaScript or Python, if you're familiar with JavaScript, you shouldn't have a big trouble understanding this. So let's take an example, and I would show the and another thing, inside the code, we are not hard coding the operation. For instance, initially we were using the plus to combine the value at the left child and the value at the right child. We are implementing the operation as just calling operation on the two values. Same when we call the range query, we are just calling the operation on the range value and the value of the element. Same here in the updates. So the point is, we are not hard coding a giving operation inside. We are passing the operation rather as an argument. It's a function. It's a function. Here, look. Here we are creating. We have an array. So we created a segment tree with that. Pardon me. Just. So we have the array that we need to support operations on. We created a segment tree and we passed a function. This is a declaration of a lambda expression. This lambda expression takes two values and returns something. Here an example. Look. For instance, that function equals x, y, and we return x. This is exactly as in JavaScript. So if we call func, on 1, 2, 3, it will just compute the product. Same if we do def func A, B, C, multiplied by C over A multiplied by B over C multiplied by A plus. No. We defined a function and we could assign a function to a variable A. So in functional programming, you could pass functions as arguments to other functions, and you could call. That's it. Especially in Python or JavaScript, this is pretty common. And just to close, let's do this. Class C def self A this self value equals A, val equals A. Okay. Let's define init. Let's define a function or a method in C called call. So by defining this this function to the class C, we are defining how C or how objects of the class C could be called on arguments. This is a mouthful, but let me just show you. So return A multiplied by V over W. So let's say C equals 45. Okay. Now A is an object of C, right? So if we by defining this this method call, we could call A, like call A as if A was a procedure. A is not defined. Oh, I made a small mistake. A is not defined. This point and this point dot value. This dot val. Let's just. Self.a, I couldn't call self.a because a was an argument, so it won't be recognized here. I could call self.value because val is an attribute of objects from class C, but a is just was just an argument to the construction. Okay. So we could call a the object a on like arguments as if a was as if a was as if a is a function. This, oh my god, I learned too many programming languages. Oh my god, damn it. Self. I tried to learn R. It was horrible. A equals C 45. Okay, A now it should work. 5 2 for instance. Oh, that's it. But this is you could anything you could define anything as a procedure. You could pass procedure as if it was you could assign function that you define as if they were arguments or values. Of course, they are called on something else. So to avoid rewriting or hard coding the operations inside the segment tree, we just pass the operation as a function, and wherever the operation is, it would be executed on inside the. So here we are defining a function that takes two arguments, x and y, and we return the minimum. Same if so let's just execute this. So let's actually print c dot. So you could see that the first segment tree is actually a minimum segment tree, where the second segment tree is just the max, and we just to switch from a min segment tree to a max segment tree, we just defined the operation. That's all. Okay. Is there any questions? One last word about the segment tree, or one last word about the standard segment tree. We initially said that the size of the array that we need to or the size of the array for which we have to answer queries should be a power of 2. So if the size of the array is not a power of 2, then we take the closest biggest power of 2. Meaning that if it's like 20, if the size of the array is n equals 20, then we take the next highest power of 2, which is here 32. How we do that? We just take the log of n. So we take ln equals the log of n, base 2, of course. If 2 to the power of log of n, or if 2 base raised to ln is equal to n, then n is actually a power of 2, so we don't have to do anything. If 2 to the power of ln is smaller than n, meaning that n is not a perfect power of 2, we would just increase n to be equal to 2 to the power of ln plus 1, meaning that we take the next smallest power of 2. So for 20, for instance, we would take 32. For 14, we would take 16, etc. You could code this in many different ways, but here this is, and here where the importance of the default value is really highlighted, because if you have a minimum segment tree, if we have a minimum segment tree and we are expanding, I just said that if the size of the array is not a power of 2, then we need to take the next smallest power of 2. So we will have elements that have no value. How to define those values? Depending on the operation, we would take the default value for those elements, because if we have a minimum segment tree, those elements that we padded the array with should be equal to default values. So for the minimum, the default value would be plus infinity. For the sum, it would be 0. For the max, it would be minus infinity. Because if we do for the min, if we do a default element equals 0, then the range query might return to us just zeros, and we don't have a 0 in actually we might not have a 0 in our segment tree, but because we defined the wrong default elements, we will just get back a 0 when we don't have a 0 actually in the array. So that's it for the segment tree. If you have questions. Yeah, but did you understand the most of it? Okay. 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 There's actually one last one last augmentation to the segment tree, which is the lazy segment tree, which enables even more operations. Well, we said that the segment tree is actually great. It's enabled updates in log n and computing the sum of the range in log n. But if we have even another query that would another type of query that would change the value of an entire range, meaning that we said that we have a first query 1 LR. That would compute, this would compute the sum. 2 IV, this would update the value at position I to be equal to V. And then we have a third query, LR V. Suppose that this third query, it could be actually 2 more queries, but let's just take one of them. Suppose that the third query would just say, for the range LR, increase every value in this range with a constant value V. So we actually have to, we could do this as multiple updates, where each update will take log n. We could solve this with, but this would be O n log n, because if L equals 0 and R equals 1, if L equals 0 and R equals 1, then 1, R equals n. Then we are updating the entire range. So for each value, we will update that value. So it would be n log n time to update the entire. So worst case, the update of a range is n log n. So this is actually a little bit bad, but there is a way to even increase or augment the segment tree to be called a lazy segment tree. And this lazy segment tree would enable updating an entire range in log n without so updating an entire range would be O log n. Updating a single value would be O log n, and updating and getting the sum of the range or any operation of the range would be still O log n. So this is actually good. And with this updates of the entire range, we cannot just update by increasing the value of the entire range. We could even assign the same value for all the elements in the range. It's the same operation basically, meaning that we have an array A, and we have a range from L to R, and we want to assign the same value, so same value V to all elements in the range, and this would be O log n. So I think rather than doing this last part, because it's included in the reading material, rather than doing it as in a presentation, I would do it as a video, and whoever is interested, I would further explain it, because we took too long in the segment tree, and we should continue into something else. But this is not very difficult. I would make an explanation for this separately. So yeah. So is there any question? Any questions? Ayman, we didn't hear anything from you. Yeah, he's one of my this is one of my students. Yeah, yeah, yeah. He's a little bit shy. Okay, so let's stop this here, and we will pick it up. I think maybe next week, or even I don't know. I actually have a little bit some problems at home. Maybe we will pick up next week or the week after. But I think next week we would do just sorting trees, but maybe I would not do it with as much reading material. I would do it with the lecture from, especially since I'm recording, I could just share the video and not do a YouTube video or something. I could just do with a lecture from another source and just explain the material. And maybe we would do interview questions from interview questions from like coding club or Ace Academy on like cases where you should use either trees or heaps, priority queues, and other stuff. So thank you for joining. Thank you to anyone that has joined, and yeah, we I hope I see you next session. Take care. We'll talk on Discord. Okay, okay. Take care. Bye.